So we were just finishing up the acid-base PowerPoint packet, and we were talking about the three buffering mechanisms. So I'm going to kind of pick up right there where we left off. So just to kind of go over this again, I know we went over this slide, but just to go over this one more time as we really get into describing these mechanisms in more detail. We talked about the three lines of defense, the buffering of hydrogen ions with bicarbonate. This is the first line of defense that we said would only limit changes in pH, as in prevent changes, but not actually reverse or correct or compensate. The second and third mechanisms were the respiratory compensation, which was the way that the lungs could chime in and change the rate of ventilation, and that would be a compensatory mechanism to reverse changes in pH, reverse changes in plasma pH. And then the kidneys had an even more hands-on role, even though it was longer, like hours to days. This had a more hands-on role in reversing pH changes. This could increase the rate of bicarbonate reabsorption and the synthesis of new bicarbonate, as well as increase the rate of hydrogen ion secretion into the urine. So the kidneys could regulate those three things in order to compensate as well. And those are the three mechanisms that we're going to get into. We describe these buffers here. And remember, a buffer is a solution that resists a change in pH. So the reason that we call bicarbonate a buffer is because it is going to join with these hydrogen ions and create carbonic acid. And carbonic acid is not going to influence the pH, the plasma pH, the same way that these hydrogen ions would on their own. So in this way, bicarbonate is buffering any pH change by adding to those hydrogen ions and creating an entirely new compound, which is carbonic acid. And then those two, this carbonic acid could freely dissociate into water and carbon dioxide, again, not influencing the pH. So this is one of the most important buffers that we have in our extracellular fluid or in our plasma. In terms of intracellular, we talked about proteins being able to buffer hydrogen ions and form another complex, and phosphate also being able to buffer hydrogen ions and forming phosphoric acid. This is really unique to the distal part of the tubule. We'll talk about this later on, the formation of this phosphoric acid. So in terms of the way that the lungs compensate, we said the lungs take minutes to have an effect, and this was basically a change in the rate of ventilation to combat any changes in blood pH. And this was detected by an increase or decrease in the blood CO2 levels, right? So the amount of CO2 that is in the plasma. So if there's excess CO2, centers in the brain would detect that, and it would increase the rate of ventilation, which would help to decrease the CO2, and the reverse is true. If there is decreased CO2 as the initial state, then again, centers in the brain would detect that and decrease the rate of ventilation in an attempt to increase the CO2 as a response. And I think we walked through this flow chart that showed that respiratory compensation already. So the renal compensation, we said, is the third line of defense. This takes much longer, so hours to days. And the way that the kidneys do this is by secreting hydrogen ions into the tubular fluid, that is to excrete it from the body, reabsorbing bicarbonate back into the plasma, or secreting, synthesizing fresh new bicarbonate and reabsorbing that into the plasma as well. And so the kidneys can increase these things if that's what the compensation would require, or decrease these three things if that's what the compensation would require as well. So let's look at what happens in the proximal tubule. So the mechanism in the proximal tubule is that the reabsorption of bicarbonate back into the plasma is exactly coupled to the secretion of hydrogen ions into the tubular fluid. And most of the filtered bicarbonate is reabsorbed. This is the way that the body prevents excess acidic states in the plasma. It reabsorbs that bicarbonate that has been filtered across the glomerulus, filtered into the plasma, because if we were to excrete that bicarbonate, then we would lose bicarbonate at a rate faster than we were then we would be losing acid, and that would put us in an excess acidic state. And so 80 to 90% of the bicarb that's filtered is immediately reabsorbed in the proximal tubule. And then the exact same hydrogen ions are going to be secreted in exchange for sodium that's reabsorbed. And we'll visualize this mechanism here in a bit. In the distal tubule, it's a little bit different. The newly formed bicarbonate can be reabsorbed into the plasma, and there's a different buffer that's used in the distal tubule. So in the proximal tubule, carbonic acid is created, and that is dissociated into CO2 and water. And in the distal part of the tubule, the buffer is different. So the buffer is phosphate ions, and that is what creates the phosphoric acid that we were speaking about earlier. So let's actually visualize or illustrate these mechanisms here. So we've got filtered bicarbonate. So bicarbonate being filtered across the glomerulus ends up here in the lumen in the tubular fluid. It's being combined with the hydrogen ions that are being secreted. And that is forming carbonic acid. And via the enzyme carbonic anhydrase, that is dissociated into water and CO2. Now the CO2 can dissolve into the cell and recombine here with water to give us more carbonic acid, again, under the influence of carbonic anhydrase. So carbonic anhydrase can catalyze this reaction in a forward and reverse direction. So it can make CO2 and water, but it can also recombine those reactants to give us carbonic acid inside the cell as well. And then that carbonic acid is dissociated back into hydrogen ions and bicarb. So all of this is just a fancy, clever way to get bicarb into the cell, okay, as we can see, as well as to buffer any changes of the pH that would be experienced by this hydrogen ions on its own. So once we have this bicarb inside the cell, it can be exchanged across the basolateral surface for chloride, and then hydrogen ions can be secreted once again to continue combining with bicarb, getting it into the cell, secreted once again. And that is how we reabsorb bicarbonate and secrete hydrogen ions in the proximal tubule. And just to point out the mechanism for the hydrogen ion secretion, it can be exchanged across the apical surface for sodium. So sodium is coming in passively, and it can be exchanged with those hydrogen ions in order for them to be secreted. In the distal tubule, as I mentioned earlier, the buffer is different. So here the buffer is phosphate. So we combined the hydrogen ions in the tubular fluid with the phosphate that's being filtered. That gives us phosphoric acid. And that is how we buffer the changes here in the tubular fluid. Inside the cell, we have carbonic acid once again being dissociated in order for this bicarb to be reabsorbed. So in the distal part of the tubule, similar mechanism that's happening. The buffer is different, so it's phosphoric acid, but we still have the reabsorption of bicarb or the synthesis of new bicarb and the secretion of hydrogen ions. Okay, we're going to skip over this slide that speaks about glutamine, so we're not going to talk about glutamine at all. And we're also going to skip over this slide that speaks about the Henderson-Hasselbalch equation for calculating the pH. We're not going to look at this at all. And we're going to move right on to looking at the compensation. So this is a more practical application of acid-base disturbances and looking at how each of these disturbances can be compensated. Now, as a rule of thumb, remember that the compensation must take place in the system that is opposite to what is causing it. So if the lungs are creating the acid-base disturbance, the kidneys will compensate, or correct. If the kidneys or other mechanisms, such as vomiting, diarrhea, anything other than the lungs, if that is creating the disturbance, then the lungs must compensate. So the first disturbance is a respiratory acidosis. And we said that the cause of this would be hypoventilation. So if you have respiratory depression, if you're not breathing or ventilating at an adequate rate, you're going to start to hold on to excess CO2. And that is going to be reflected as a respiratory acidosis, right? Your plasma pH is now going to be very low as that excess CO2 creates an acidotic effect. So the compensation here needs to be in the lungs, right? It's being caused in the kidney, it's being caused in the lungs, excuse me, it needs to be compensated in the kidneys. And so what the kidneys will do to compensate for a respiratory acidosis is increase their rate of hydrogen ion secretion, so increase the dumping of hydrogen ions into the tubular fluid, as well as increase the rate of bicarb reabsorption, so increasing the rate of bicarbonate moving across the basolateral surface into the plasma. And as we can see, bringing in more base will correct that acidic state, but also dumping more acid will also help to correct that acidic state. Okay, let's talk about a respiratory alkalosis, so the exact opposite here. This is being caused by hyperventilation. And so one of the prominent examples is a panic attack. So during a panic attack or an anxiety attack, you're hyperventilating, and that is going to create a state of blowing off excess CO2. And so that puts you into a respiratory alkalosis because now you're losing more CO2 than you need to, and your plasma pH is going to start to rise, it's going to become more basic. The compensation, again, must take place in the kidneys because the causatory mechanism is happening in the lungs. So the way that the kidneys will compensate here is decrease the hydrogen ion secretion, so decrease how much hydrogen is being pumped into that tubular fluid, as well as decreasing the bicarb reabsorption. And these two mechanisms in and of themselves will help to correct an alkalosis, right? So if we decrease the amount of base that's being reabsorbed into the plasma, that is going to correct an alkalosis. If we decrease the amount of acid that we're losing, we're holding on to more acid, that is also going to correct an alkalosis. Okay, so let's look at the metabolic disturbances. So again, the metabolic disturbances are created anywhere other than by the lungs. So anything that is independent of CO2 that is causing an increase in hydrogen ion secretion in the plasma is going to create a metabolic acidosis. And so some of the things that we talked about would be if you're holding on to more acid, so if you're eating a diet excess in proteins or a diet excess in fats that are broken down to create excess acid, or if you are exercising quite a bit, so your muscles are burning energy and are creating lots of lactic acid, that can also be a source for metabolic acidosis. So the compensation here needs to be in the lungs, okay? The lungs, and unless there's a kidney problem, the kidneys can chip in as well. So respiratory compensation is going to be increased ventilation, right? So that's going to help to blow off more CO2 and decrease the plasma acidity. The compensation in the kidneys is going to be increased bicarb secretion, increase acid secretion, increase bicarb reabsorption, and then increasing the synthesis of new bicarbonate in the proximal tubule. And then the opposite is true here. If we have a metabolic alkalosis, which is caused by a decrease in the plasma hydrogen ion concentration that is not involving the lungs, the compensation will be in the kidneys and the lung unless there's lung issues or lung problems. The lungs will decrease ventilation in order to hold on to more CO2 to correct that alkalosis. The kidneys will decrease hydrogen ion secretion, again, holding on to more acid to correct that alkalosis, and then decrease bicarb reabsorption so that we get rid of that base, or decrease the synthesis of new bicarbonate. Okay. So the mechanism is going to be the mechanism of compensation, I should say, is going to be the opposite for the causative mechanism, unless there's some type of problem or issue in the kidneys that would prevent the kidneys from compensating. So this flow chart here at the end is a good summary of all of the acid-base disturbances and the compensations. And so this is a good reference chart for you to look at if you're trying to figure out the disturbance or if you're trying to figure out the compensation. So we start off by looking at the pH. And if the pH is too high or too low, we then look at whether it's an acidosis or an alkalosis. So if the pH is less than 7.35, we know it's an acidosis. If it's greater than 7.45, we know it's an alkalosis. From there, we can then determine the cause of the acidosis and the compensation. So if we look at the bicarb and the PCO2, then we can deduce the cause of the acidosis. So if the bicarb is low, less than 24 millimoles, or if the PCO2 is high, less than 40, we can determine the cause of that acidosis. So it's either a metabolic acidosis if the bicarb is low, or a respiratory acidosis if the PCO2 is high. And again, like I said earlier, if the cause is happening in the lungs, the compensation is going to be in the kidneys. If the cause is happening outside of the lungs, the compensation is going to be happening in the lungs. Okay, and then that will bring about a correction. If the compensation is in the lungs, it's going to correct the acid-base disturbance by changing the rate of ventilation, which will correct the CO2. If the compensation is in the lungs, it's going to change the rate of hydrogen ion secretion as well as bicarb reabsorption, and that will correct the initial acidosis. Okay, and the same is going to be true for the alkalosis. Again, we're going to look at the bicarb and the PCO2 to determine what the cause of the alkalosis is. If the bicarb is high, right away we know that the cause cannot be in the lungs. It must be metabolic, right? So think about things like vomiting, where we're losing excess acid. That's going to create a state of metabolic alkalosis. And the compensation will have to be in the lungs, which will change the rate of ventilation in order to compensate for that metabolic disturbance. And if the cause is in the lungs, that's going to indicate itself by having a lower than normal PCO2, and that's going to be compensated in the lungs by decreasing the rate of bicarb reabsorption or increase the rate of acid secretion. So this is not something for you to necessarily memorize. You can always refer to it. So let's say I give you a patient. Let's say I tell you I have a patient. I will give you the patient's blood pH. Let's say it's 7.25. Right away, you know that's an acidosis. I will give you the patient's bicarb. Let's say it's 25, right? So it's normal bicarb. But let's say I tell you that their PCO2 is greater than 40. So let's say 45 or 46. Right away, you can diagnose that that patient has an acidosis that's being caused in the respiratory system because the bicarb is normal, but the PCO2 is high. And so it's a respiratory acidosis. And if I go a step further and ask you about the compensatory mechanism, you should be able to tell me that the compensation would happen in the kidneys, and the kidneys would reabsorb more bicarb and secrete more hydrogen ions to compensate for that respiratory acidosis. So again, something you should be able to refer to and use this to be able to make diagnoses about a patient given the values.